So for this video, what we're going to be talking about is the concept of weighted averages. So the idea of weighted averages is that if you take multiple measurements, we're all really used to finding the average of that value. So what we say is that if all the uncertainties, let's say, if all the uncertainties are equal, then the best estimate of some value that we measure multiple times would just be the average value, which we define as 1 over n times the sum of all of those averages. But what this video supposes is, what if the uncertainties, or the sigmas, are not equal? So this might have been not something that you haven't really thought about in the past, but if you have multiple measurements of some value, and some of them you're more sure of than the other ones, it would make sense that you wouldn't just combine them all together and give them each equal weight. So if you think about, for example, the experiment that we all just did where we measured G like a week or so ago. Let's say there's two groups. Let's say there's my group and Dr. McGowan's group. So this would be an example for measure G. Let's say Dr. McGowan and I both do this. And when I did it, I'm super good at experiments. So I got a value that was 9.7 plus or minus 0.1 meters per second squared. So this is like first measurement. And let's say Dr. McGowan did it, and he got interrupted in the middle, and some of his data looked a little weird. And when he did it, he got, call this G2, he got a value of 16 plus or minus 6 meters per second. So then you could say, all right, we have these two measurements of this one value, why don't we combine them? And this makes sense. I mean, if everybody in this class did this experiment, we might as well just pool all of our answers together. But if you look at those values, you wouldn't say that you're just as sure as Dr. McGowan's as mine, not only because my number is closer than the real answer, which it is, but also because of the fact that his uncertainty is so large. The uncertainty in G2 is more than 10 times larger than the uncertainty in G1, and it's also fractionally really large. So what you have to do is you have to define something called the weight. So let's say we have multiple measurements. I'm going to be a little formal now. Say we have multiple measurements. So you have x1 plus or minus sigma 1, you have x2 plus or minus sigma 2, etc. So we have all these different measurements. What we do is we define something called the weights. We define the weights as Wi, so the individual weight is just equal to 1 over the individual uncertainty squared. So this is the uncertainty. This one right here. So sigma is the uncertainty. Sigma I is the uncertainty in xi. Oops. So you just define something called the uncertainty, and then what we do is we define something called the average, the weighted average, as the sum of those individual weights. So you weight each point by how certain you are by it, divided by, and then you normalize by those weights at the end. Sorry, I'll scroll down again. Divided by the sum over all of those weights. So you define the individual weights as 1 over the uncertainty squared for the individual values, and you define the weighted average as you sum those weights times the value, so you're kind of weighing the value that has the smaller uncertainty. So the smaller uncertainty will have the larger W. So you're weighing, in that bottom equation, you're weighing each value by its uncertainty. So the smaller uncertainty has the larger W, and then at the bottom you have that sum over the W's just to kind of normalize it and get you back to the correct units. There are more sophisticated derivations of this, but I'm just kind of giving this to you for use. So let's look at those values I gave you before. So we had these two values. We had G1 that was 9.7 plus or minus 0.1. I'll be good and put on my sig figs, or my units. And then we had G2 is equal to 16 plus or minus 6. So if we wanted to find the weighted average, what you would do for this is you would say, okay, well, the x, call it weighted average, is going to be 9.8 divided by 0.1 squared plus 16 divided by 6 squared divided by 1 over 0.1 squared plus 1 over 6 squared. And if you do this, you get a value of 9.702. Oops, sorry, this wasn't 9.7. So basically, it's just saying that that one data point is what we weigh everything by, and we almost don't even consider the 16. You almost ignore the larger value. If we did it the old way, probably should have done this first to convince you, but the old way, you would just say 9.7 plus 16 divided by 2. You just say, okay, let's just average them, and you get 12.85, which is a value that is kind of, again, right in between them. But of course, we know the 9.7 value, not because it's closer to the right value or anything, but it has that smaller uncertainty. You weigh it better. So again, here you basically ignore that larger value. The next question you might ask me is, every time you take any measurement in this class, you have uncertainties. So you might ask me what the uncertainty is, and this one I'll just give it to you. So you define the uncertainty, sigma of the weighted average, as just equal to 1 divided by the square root over the sum of the individual weights. And that's it. So you could get this from the previous expression just by doing some error propagation and taking some derivatives, but I'll just give it to you here. It kind of makes sense. It makes sense if you reconsider the fact that we define the weights as 1 over the uncertainty squared of the individual values. So if you rewrite this, you would get sigma I is just equal to 1 over the square root of the individual. So the individual uncertainty is that. And so if you look at these two equations, they look really similar. So this is to be used anytime you're taking an average of numbers and they have unequal uncertainties. This shows up, especially if you're comparing between groups, but sometimes if you're taking the same measurement multiple times in different regions, you might have to use different tools. So sometimes you might, let's say you're measuring a distance. Sometimes it's really large and you have to use like a meter stick, and that has a certain uncertainty, usually probably like 0.5 millimeter or something. But let's say you're also measuring something that's really small, and you get to use the calibers, and those would have a much smaller uncertainty. If you want to take those two measurements and average them, I'm not sure why you measure a super small thing and a super large thing, but let's just consider it as a situation where you have different tools. You would have to use weight uncertainty. Or if you're using different pieces of equipment to measure stuff at different times. Let's say one day you come in and all you have is a really bad, not bad, but one of those small handheld multimeters, and the other day you come in and you get to use a really nice, precise Keithley meter. You might have different uncertainties, and if you take those, you'd have to take different averages. So for the second part of this lecture, I'll be talking about counting experiments. So this is the case if you have any kind of measurement you're taking where you're counting a number. So this could be, some examples of this could be radioactivity. So if you have a nucleus that's decaying kind of at a random value, you have some average number and you have fluctuations around this, but you're counting a specific discrete quantity. Births in a given time. So if you look at births, let's say you have 100 births a day in some city, probably smaller city, what would be, how do you determine the uncertainty on that value? Something else is, it could be like cars driving past an intersection, anything like that. So anything that is counted and random. So I won't define what random is here, and this is something that I could give you a much more sophisticated derivation of, but I will just give you the result here. That if you get some value x, so you count some value x, the uncertainty on that value, sigma, some value, is just the square root of that value. And it is super simple. So any value that you count, so if I said that some city had 100 births in a given time period, maybe a day, the uncertainty on that value, so you're not actually sure. So you counted 100 births in some day, but the next day could have been something different. It doesn't have to be 100 on a specific day. So you're going to have some uncertainty in that value. And so the uncertainty is just the square root of the number you see. So it would be 100 plus or minus 10. Super simple. If you count some experiment and you have the average value, so let's say instead what you did was you measured the births every Monday for in a given month, and you average those values together. You'd say, okay, what's the uncertainty on that average value? Well, it's just the uncertainty of the average value. So it works for an average value that you obtain through counting an event multiple times, or it works on an individual count that the uncertainty in a count is the square root. So both this and the weighted average, they're not really related, but they're both useful tools for when you're doing experiments. You might find yourself needing them in specific cases, and this is how you apply more sophisticated error analysis to them.